Good afternoon. I hope you're enjoying this great day. Won't last. It is Minnesota after all. Welcome to the last week of Humpky's Office videos. Today I'd like to talk about something called general vector spaces. This has nothing to do with the military. And when I have a class, I'm with a class. I have a class now, but I'm not with you guys. But when I am, the way I do this is generally this. I let P2 equal the collection of all quadratic, that means second degree, polynomials. So this is going to be what we look at now. And what I ask for usually right now is somebody give me an element in this space. So nobody's here to do that. I'm here, I can do it. Oh, okay, Snow, give me an element to this space. 5. No, well, not exactly what I mean. I mean a quadratic polynomial. In a way, 5 is okay, but it's not what I'm looking for. This is one, but I'm not exactly looking for that. I'm looking for something else. Like another number? No, not like another number, like something else. X squared. Yes, very good, Snow, very good. I thought of it all myself. Whatever. Okay, x squared is in P2, and now there are more. Can you give me another one? X squared plus 4. Yeah, that's one. Something else, a different one. X squared plus 2x plus 7. Yeah, that's another one. All of these are in P2. Can you give me something that's not in P2? Sin x. Yeah, that's right. Sin x is not in P2. Or lots of other things are not in P2. The vector 1 minus 1 from R2, that's not in P2. And lots of things are not in P2. But also here's another one, x cubed plus x plus 3. This is not in P2 because it's a cubic. Now this one actually is, even though it's missing the x in the constant term. And this one actually is because it means no x squareds and no x's plus 5, and this is okay. So now we could look for the general form of something from P2. And a general form might be something like ax squared plus bx plus c. Anything like this is in P2 where a, b, and c are any real numbers. So this is the general form. And P2 is actually equal to this if you write it out in mathematical language. Now, notice here that we have written something in the language of span. Since these can be any real numbers, we could use our language developed for linear algebra. These are called the real vector spaces, are R's, R1, R2, R3 are real vector spaces. This is a general vector space, but we're going to use the same language. This is the span of 3 things, x squared, 3 specific polynomials, x squared, x, and 1. So if we take the span of these, what does this mean? It means all multiples of the first plus any other multiple of the second plus any other multiple of the third, all possible multiples of these three. So you can write P2 as the span of these three. And so consequently, we might say that these three by themselves, x squared, x, and 1, are a basis for P2. Oh yeah, we got to check whether they're linearly independent. Thanks, Ohm. Are these linearly independent? For example, is x squared linearly independent of x? What would that mean? So I'll erase some of this stuff and work up on top now. Can you solve this? Ax squared plus bx equals 0. So we want to see, is the only solution to this 0? Now, the important thing here is what does 0 mean? This is a 0 function. This means the function y equals 0. Its graph is the x-axis. Just like this x squared means the function y equals x squared. It's a quadratic polynomial, so it's a function. Its graph is a parabola. And this guy here is the function. This means the function y equals x. So this is a straight line of slope 1. And so this equation doesn't mean solve this for x. This means that these are particular functions and you want to get the 0 function. Well, notice that if either one of these, a or b, is non-zero, if a is non-zero, then this is going to be some kind of parabola. If a is 0 and b is not 0, it's going to be some kind of straight line, and b is going to be its slope. The only way that you can get the 0 function is if both a and b are 0. Now, a and b are just constants, but x squared and x are not exactly unknowns here. They represent these two functions. So we want to know if you add a times this function plus b times this function, can you get the 0 function? No, you cannot get the 0 function unless a and b are both 0. So these are also linearly independent. So these, as Ohm points out, these are a basis for P2 now because they are linearly independent and they span P2. This is called a general vector space. And what is the dimension of this vector space? What is the dimension of this particular vector space? Ohm is into this stuff. 3. Yes, exactly. The dimension is 3. Same as my age. Yeah, same as your age, Ohm. Because there are 3 things in a basis, this is a 3-dimensional vector space. So P2 is a 3-dimensional vector space. It has a basis of 3 things. Let's erase this and try a couple other things. I'm going to call this coding for P2. Now, rather than coding, this is not computer coding, so maybe I should write encoding. I want to kind of encode this information that we have. So I need an element of P2, just some element of P2 just to show you how to encode this. Quail? A little more complicated, Quill. Yeah, that would do. So let's take this one. So we'll take the function x squared plus 2x plus 3. So there's a function x squared plus 2x plus 3. Is it a quadratic polynomial? Yeah. So it's one of the things we're talking about. This is one of the functions in P2. We could graph it, but in a way, we're not interested in graphing right now. We're kind of interested in this information. So we're going to take the standard basis for P2, x squared, x, and 1. And actually, this is the order that it usually is, highest from lowest for the standard. This is P2 here, and this is its standard basis. The dimension is 3. I'll put a little tag on there just to remind myself. Dimension equals 3. And I'm going to take the real vector space, R3, with its standard basis, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. That's its standard basis. And I'm going to, this is not a change of basis because we have different spaces here. So this is also, by the way, dim equals 3. But I'm going to encode this in the following way. If somebody here is of the form, and that's why I used F here, we're going to encode quills will be 1x squared, 2 x's, and 3. So if we are looking at the standard basis, but in P2, 1, 2, 3 means this function. 1, 2, 3 means one of these plus 2 of these plus 3 of these. And I'm going to encode that with 1, 2, 3 with the standard basis over here. Now you might say these look pretty the same, except this one is rust and this one is green, but they're quite different because this standard basis is this, and this standard basis is functions. But in a way, they are the same. So this is the encoding function. I'll call it E, which looks like the identity. 1, 2, 3 maps to 1, 2, 3, but it is not exactly the identity. But the structure is the same. If you add 2 guys over here, that the coded versions, you will add 2 guys over here. The same kind of thing. So if you look at F1 plus F2, then it gets encoded by the encoding for F1 plus the encoding for F2. So the algebraic or arithmetic is the same in both, but these are polynomials and these are real vectors. And that's what it means to have an abstract vector space, that you're dealing with something that has all the properties that we have over here with vector spaces, but they're not real numbers. They are other things, like in this case, polynomial. P2 is a 3-dimensional vector space. This is its basis, and it works the same here. Now, so this next chapter, what we're just going to deal with this week, is all about this stuff. And the first question is, what do you mean by an abstract vector space? What do you have to make it an abstract vector space? That is sort of the definition. So these are the requirements of an abstract vector space. One, if x1, maybe I'll call it u1, if u1 and u2 are in this abstract vector space, then so is u1 plus u2. And I'll use a circle plus because this plus is sometimes defined in a weird way. So addition of these vectors might not look like addition of numbers, but there is some operation called addition, and it works like this. And this is called closed using this plus operation. Add any two, you get another one. So it must be closed using addition. Secondly, if U is one of the elements of this abstract vector space, and S is any real number, so they're connected with real numbers by these scalars, then S times U is also one of the elements of the abstract vector space. And this is called closed using scalar multiplication. So you've got to have two operations that look just like addition and scalar multiplication, although they can be defined so that they look deceptively different, but they have to work like this. So those are the first two. These are in the book, so you don't have to write them down. Take notes on this, or you could just stop and take a little notes. The third one is there is a zero. And that zero is usually called the zero vector, but this does not mean number, zero. I could have used Z, but nobody does that. Everybody uses this symbol. So the abstract vector space must have a zero. Now, when we were doing P2, and Snow gave me 5, the number 5 is also equal to a function 5. F of x equals 5. F of x equal 5 is the graph. You go up 5 units. There's its graph. So this looks like a number when Snow gave it to me, but it's not a number in this context. It's a function, and that's its graph. And in a similar way, for excuse me, in a similar way for the abstract vector space P2, the zero function, or the y-axis, the x-axis, is a function. So this is the zero is a function, and this is often how things look. Even though it looks like a number, it doesn't mean a number. In P2 case, it means the zero function. But it has a specific property, such that means it has to do this. If U is any vector in the abstract vector space, then U plus 0 is U. And also 0 plus U is U. So closed under additions, closed under scalar multiplication, it's got a zero element, and basic arithmetic. Now, there are about 6 of these basic arithmetic rules. For example, one of them is U plus V equals V plus U. This is called commutativity of the addition operation. And there are others. But what I would like you to be able to say is, if I ask you what is the definition of an abstract vector space, you will say it's closed under addition, closed under scalar multiplication, has a zero element, and satisfies basic arithmetic. So those 4 things. And we're going to look at some specific examples. One is P2, and then others like that, P1, P3, P17, polynomial vector spaces. A second one is matrix, m sub little m by n. This means all m by n matrices. This is also a vector space, an abstract vector space. And the third one we'll look at is, usually it's like this, C01 equals all continuous functions on 01 with the domain 01. Maybe I'll put one more down. D of 01 equals all functions which have derivatives, which are differentiable. That means you can take the derivative. So these are basically the four that we'll look at. All of these are abstract vector spaces. I might point out that this list continues down. I mean, this list is huge about what things can be abstract vector spaces. So if we continue the list this way, it doesn't take long before Yang notices the list, or Narumi or James notices the list. And the list turns around and comes back. I mean, it's got billions of things. And because the structure of vector spaces is, of the real vector spaces that we've looked at so far, are like so many other things that mathematicians and scientists study, that the list just is long. But we'll just look at these to focus in on these just a little bit. And I'll give you a few homework assignments with some of these to do starting next time. And we'll finish out the course looking at these abstract vector spaces. In any case, I hope you have a good rest of the weekend, and I will see you Monday. Don't forget the makeup exam if you want to take it. It's up and ready to go. Have a look, and I'll see you on Monday.